Okay, in this presentation we're going to look at confidence intervals. And what we're going to look at is the difference in proportions from two samples, which is essentially difference in proportions, just to give it a name. A researcher was investigating computer usage among students at a particular university. 300 undergraduate students and 100 postgraduate students were chosen at random and asked if they owned a laptop. It found that 150 of the undergraduates and 80 of the postgraduates owned a laptop. So the exercise is find a 95% confidence interval for the difference in the proportion of undergraduates and postgraduates who own a laptop. And on the basis of this interval, do you believe that postgraduates and undergraduates are equally likely to own a laptop? Okay. So, straightforward enough, probably a little bit outdated in terms of numbers. Probably many students have laptops these days. But anyway, so let's calculate the 95% confidence interval for the difference in proportion. Now, the important thing here is that we have to do a calculation called a standard error. So, this is a key part of the calculation, and it's probably the most complex part. So I won't get into what a standard error is, but just to sort of say it actually is sort of gives a measure of uncertainty about the data that we have. Okay, so standard error of p hat 1 minus p hat 2. Okay, those are the sample proportions, and we'll just discuss those shortly. Is the square root of p hat 1 times 1 minus p hat 1, which is the complement of p hat 1. So the p hat 1 times 1 minus p hat 1 divided by n1, that's the sample size for that corresponding to that sample, plus p hat 2 times 1 minus p hat 2 divided by n2. So again, that is the sample proportion and sample size from the second sample. Okay? So, complex enough, you probably will be given this formula at the back of an exam paper because it is the crucial part of the exercise. Okay. So in general, what we have to do is calculate the confidence interval. So this is the full formula here. So we have the point estimate, which is the difference in proportions. So it's the proportion from one sample minus the proportion from the other sample. So it's the difference in proportions times plus or minus z, which is the quantile from the standard normal distribution, times the standard error. So it's point estimate plus or minus quantile times standard error. And I've just discussed standard error there previously. So P1 hat and P2 hat are the sample proportions again. And also we have our values. N1 is the sample size, number of undergraduates. N2 is the number of postgraduates, which is 100. X1 is the number of undergraduates that own a laptop, and X2 is the number of postgraduates that own a laptop. Okay, and P hat 1 and P hat 2 are the X1 divided by N1. This number of successes divided by the sample size in each case. So P hat 1 equals X1 divided by N1. 150 out of 300, that's the undergraduate students. 50%, 0.5. For the postgraduates, P hat 2, we have X2 minus N2. 80 postgraduate students own laptops out of 100 postgraduate students. That is 0.8, 80%. And the difference in proportions is our point estimate. Okay, so we have p hat 1 minus p hat 2. 0.5 minus 0.8, and that is equal to minus 0.3. Now really, it doesn't really matter which, if you go postgraduates first or undergraduates first. So you could actually make that 0.3 and just have the postgraduates as the first sample and undergraduates as the second sample. I just stick with this way just to be consistent with what I've done before, but really it's not a big deal if you swap it the other way around and go 0.8 minus 0.5. Okay, it'll just change how you interpret things in the long term. We are looking at things here from the point of view of undergraduates. Okay, so moving on to the big bit of the calculation. calculating the standard error. So the standard error, again, is the square root of p hat 1 times 1 minus p hat 1 divided by n1. So essentially we get our point estimate, multiply it by the complement of that point estimate, and divide it by the sample size for both cases, and then we add them together and then get the square root. It's straightforward. 0.5 times 1 minus 0.5 divided by 300 plus 0.8 times 1 minus 0.8 divided by 100. Okay, so we get 0.5 times 0.5 divided by 300 plus 0.8 times 0.2 divided by 100. So essentially we end up with the square root, and not forgetting the square root of 0.25 divided by 300 plus 0.16 divided by 100. Now the numbers here can get very tricky to work with. We can end up with quite a lot of decimal places there. So 0.25 divided by 300 ends up as 0.000833. So plausibly we could end up with as many as 6 or 7 decimal places in this part of the calculation. Nothing we can do about it. Usually we try and avoid that as much as possible, but in this type of work we probably just better off temporarily going with it as much as possible. So we end up with the square root of 0.000833 plus 0.0016, and we get the square root of 0.002433, and that ends up as approximately 0.04932. Okay, so rounding error comes into this a lot. So if you get a number that's close to that, which is approximately about 5%, 0.04932, that's good enough. Okay, so the margin of error is the quantile times the standard error. Okay, margin of error equals Z times S of E, SE, which is 1.96 times 0.0493, which is approximately 0.0966. Now, the quantile of the 95% confidence interval is 1.96. Okay. Now, so if you're unfamiliar about where this 1.96 came out of, it is the quantile of the standard normal distribution that corresponds to a 95% interval in the middle. It actually corresponds, it's the quantile for the 97.5 quantile of the standard normal distribution. Okay. Now, if you're unfamiliar with that, you're probably going a bit too far, and you need to backtrack a bit and figure out where this 1.96 comes from. It comes up quite a lot in these confidence intervals and hypothesis test questions, so you need to know it. You need to be sure about where it comes from. I'm not going to deal with it here. I'm sort of assuming that you already know what is going on with it. Okay. Anyway, to sum up, the 95% confidence interval for the difference of proportions is minus 0.3 plus or minus 0.00966, which is minus 0.3966 to minus 0.2034. And again, that's from the point of view of the undergraduates. If you were looking from the point of view of the postgraduates, you just reverse that. You get 0.20 to 0.39. Okay. So I think that's it. Oh yeah, since the confidence interval, so we have to interpret it. Since the confidence interval for the difference of proportion does not include 0, we can conclude that there is a statistically significant difference in the proportion of undergraduates and postgraduates who own a laptop. This implies that undergraduates and postgraduates are not equally likely to own a laptop. Okay, so essentially we're looking at that confidence interval there and seeing is 0 in that range of values. And again, if you reverse, looking at it from the other point of view, from the point of view of postgraduates, 20% to 39%, that's a difference in proportion the same way. 0 is not in that either. So essentially, one set of students is way more likely to own a laptop as compared to the other group, according to this data. Now, I think we're done. Yes, we're done there. Okay, we'll leave it there.